The hydrogen bonding intermolecular force is actually quite important, especially when you start getting into organic or biological chemistry. Hydrogen bonding is a special case of a dipole interaction. In the previous section, we talked about how polar molecules have a dipole and they create a dipole intermolecular force. So here we're going to be taking that idea and making it even more extreme to create a stronger intermolecular force called hydrogen bonding. The molecule to have hydrogen bonding must contain an OH or an NH or an FH bond. If it doesn't have one of these bonds, it is not considered to be able to form a hydrogen bond with itself. So it's actually very easy to look at a molecule and say, does it have a hydrogen bonding intermolecular force? If it has one of these bonds, yes. If it does not, no. So why is hydrogen bonding different than other dipole interactions? And this has to do with the fact that we are dealing with three of the most electronegative elements in the periodic table: oxygen, nitrogen, and fluorine. When we were talking about dipole moments inside of bonds, remember we said that if a covalent bond is being shared between two atoms, the more electronegative atom is going to be pulling the electron closer to it and away from the other atom and creating a partial positive and a partial negative charge. So that's what created a dipole interaction inside of a polar molecule. But now, because we're dealing with some of the most electronegative elements, this dipole separation is actually so strong that the bond, so the bond here between hydrogen and fluorine, is actually weak enough to allow one hydrogen to pop off one fluorine and jump on to another fluorine. This is a very important idea, that if you're dealing with something that's hydrogen bonding, if you're looking at a molecule that has a hydrogen bond, those hydrogens are not permanently attached to that atom. So if we have an OH bond, that hydrogen is not really permanently attached to the oxygen. The hydrogen pops off and actually moves around in the solution that we're dealing with, and then it jumps back onto the oxygen. So this bond that we're looking at, this OH, NH, and FH bond, is so polarized that the fluorine can jump off. So what happens here, if we have multiple HF molecules inside of a liquid, this negatively charged fluorine, so this bond's polarized, the electrons are pulled close to the fluorine, it has a slight negative charge. It's so strong that it can actually pull this hydrogen away from this fluorine. So this bond is very polarized, the electrons are closer to this fluorine. So it's almost like this slightly positively charged hydrogen are being shared in between these two fluorines. That's because this bond is so polarized. So in reality, this fluorine is kind of grabbing onto this hydrogen, this fluorine is kind of grabbing onto this hydrogen, and this continues on. So you can see the process repeats itself. So all of these molecules are very tightly bonded together through an intermolecular force because these hydrogens are actually being shared in between them. So this is really a dipole interaction, but it's even more extreme. So when we had a dipole, the atoms didn't move around. Here the atoms are being moved around. So literally the fluorine from one HF is sharing a hydrogen with another HF, and that causes a very, very strong interaction between them. And that's what we call our hydrogen bonding intermolecular force. So like I said, this is very easy to see. If I give you a molecule, and this is one of your skills, is if I show you a molecule, you should be able to tell me, does it have the hydrogen bonding intermolecular force? And really it says, does it have an OH, NH, or HF bond inside there? If the answer is yes, it does have hydrogen bonding. If it's no, it does not. When I look at this first one, and this is where people get fooled, yeah, it does have an oxygen and it does have a hydrogen, but the oxygen and the hydrogen are not directly bonded together. So this is not hydrogen bonding. We look at water, and water is kind of the poster child for hydrogen bonding here. We have an oxygen directly bonded to a hydrogen. That means that it's hydrogen bonding. Here with this last one, this is ammonia. Yeah, it has a nitrogen directly bonded to a hydrogen, so it is also hydrogen bonding. It has the ability to create a hydrogen bonding intermolecular force with itself. So it's that simple. It's very easy to be able to look at something and say, does it have a hydrogen bonding intermolecular force? So this first one, no, because there's no hydrogens bonded to oxygen, nitrogen, or fluorine. Number 2 and number 3, yes.